Welcome back, 3.3 part 2. We had just been talking about revenue functions that we're going to come up with ourselves, keeping in mind that revenue is always just the number of items sold times the price per item. And in this case, we're going to be having them both changing, but in a related way. So not just randomly changing, but there's going to be a relation given. And I'm going to, again, I'll emphasize the books method. There is at least one other method for doing these problems. You might find videos out there, and let's talk about it. If you like the other method better, I'm totally good with it. And in fact, I've used a textbook in the past that uses this other method, but I'll follow our books method. Example number 16. A charter flight club charges its members $250 per year. But for each new member above a membership of 65, the charge for all members is reduced by $2 each. What number of members leads to a maximum revenue? So as soon as I see maximum, that tells me I'm going to be solving the derivative of r equal to 0, r prime equal to 0. And all we have to do is get our revenue function. So we do have some starting information. When there are 65 members, they each paid $250. So our starting revenue would be 65 people, that would be the number of items, memberships, times $250 per membership equals $16,250. So that's the current revenue. Let's see if we can do better. Now, we will assume we get n additional members. So our new number of members will be 65 plus n. Okay, that's going to be the number of items, the changing number of items. And then when this happens, everybody starts paying less, depending on n, the number of new members. Watch this, how this happens. The actual amount each person pays will be 250 minus 2 times n. That's showing the price going down for each new member, going down by $2 specifically. That's why there's a 2 in there. All right. And if you can't really see it, but there's actually a 1 in front of it, in front of the n and the number of items, the 65 plus 1 additional member at a time. We're not going up by 5 members at a time or 10 members. We're going up by 1 member at a time, and then the price goes down $2 at a time. So now our new revenue function will be the number of items times the price per item. And that's what we want to maximize. So here we go. Our variable is actually n, and we could multiply out. I'm going to use the product rule. Why not practice it? That's u times v prime, or u prime v plus u v prime. So we'll do that on this particular function. So r prime, maybe on this first example, I'll write it out. So we're going to take the derivative of 65 plus n and multiply that by 250 minus 2n. Plus, now we leave the 65 plus n alone, and we multiply by the derivative of 250 minus 2n. So working on that, derivative of 65 plus n is just a 1 from the 1 times n. 65 goes away, and then the 250 minus 2n is there, plus 65 plus n, and that's going to be multiplied by, let's see, the negative 2 is what's left over. The 250 goes away, and we get a negative 2 from the 2n. We're going to be setting that equal to 0. Let me go ahead and work out the distributions, combine like terms, all the usual stuff. So we end up with 250 minus 2n minus 130 minus 2n equals 0. Now those two n's aren't canceling. We're going to combine them. Negative 2 and negative 2 is negative 4. And then we can also combine the numbers. 250, take away 130, and we get 120 minus 4n equals 0. 120 equals 4n, divide by the 4, n is equal to 30. Now that's not the final answer. We should not, that's not either a number of memberships or a price. What that is, if you recall, is the number of additional members, right? So we should add, or we should accept 30 additional members. So there will be 95 members. 65 plus 30 is 95 members paying. How much will they be paying? 250 minus 2 times that 30. Wow, what a deal. They're going to take off $60 and each person only pays $190 now. So that's a pretty good deal, down from 250. And then the new revenue, which we now think is a maximum, would be 95 people paying $190 each is $18,050. So yeah, it's certainly more. We could do a little work if we want to about showing that we have a maximum, but I don't think I'm going to take the time on this particular problem. I'm also out of space. You could do a quick sign chart, look at values less than 30 on your derivative. Let's see, here's our derivative here, 120 minus 4n. If I plug in a number less than 30, I know that this will be positive, so we're increasing. And if I plug in a number greater than 30, this will end up being negative. And so the function will be decreasing revenue. So yes, we do have a maximum. All right, let's try the next example. It'll be a similar kind of a setup, only now we have a motel. And normally it rents 200 rooms per day at a charge of $80 per room. And now look at this. We're going to increase the price. Here's an increase, $5 increase in price corresponding with 10 fewer rooms. So we've got a price that we're going to match up with a price, and we've got rooms that will match up with rooms. Got to make sure we get the numbers lined up correctly. So if you're curious, let's check the current revenue. Why not? That would be the 200 rooms that we can rent times $80 per room, and that would be $16,000 per day. That's what we can make. Maybe we can make more by raising the rent, but renting fewer rooms. Okay, let's try it out. So our new revenue function, let's see, we're going to, it's a little bit backwards. We were given the price increase first. So the rooms are going to go down. So I'm going to subtract off something from the rooms as I increase the price. So notice I'm subtracting off for getting a fewer number of rooms, adding on a price. So the price is going up by $5 in lumps of $5. So the price is going to go up by 5n. And then the rooms are going down in bunches of 10. Each of those $5 increases. Each time we have an increase of 5, we lose 10 rooms. So I'm going to set up my revenue function this way. 200 minus 10n equals 80 plus 5n. And then n will tell us how many times to raise the price and then therefore lower the rooms. So I'm going to take the derivative of this and set it equal to 0. Again, I'll use the product rule. Can we go right into it this time? I'm going to take the derivative of 200 minus 10n, get a negative 10, leave the 80 plus 5n alone. And then on the other side, I'll leave the 200 minus 10n alone, and I will multiply by the derivative of 80 plus 5n, which is just a 5. All of that has to equal 0. All right, working that out, distributing, combining like terms, I'm going to get negative 800 minus 50n plus 1000 minus 50n. You'll see some patterns happening. Got some like terms to combine. We've got those negative 50n's to combine, got some numbers to combine. So we get 200 minus 100n equals 0. So 200 is equal to 100n, divide by the 100, and n is equal to 2. And again, that's not the final answer. That is the number of times we want to increase the price by $5. So let's see here. The new price will be 80 plus 5 times that 2. So that's 80 plus 10 would be 90. So we're going to charge $90 a room. The new number of rooms is the original 200 minus 10 times that same change of 2. So we're going to lose 20 rooms in the process. We're going to only rent 180 rooms. And then the new revenue, hopefully it'll be more than that 16,000, will be 90 times the 180 equals, okay, not too impressive. We get $16,200 now. So a little bit of an increase for one day. You know, is it worth it? Maybe. that we're not making judgment calls here. We're just doing the math. So there you have it, a new price, a new number of rooms, and a new revenue. Now, maybe on this problem, because we have just a couple more minutes, is I'll just confirm that we have a max. So using the first derivative, we could do a sign chart on either side of n equals 2, and we're looking at r prime. We know that at 2, the derivative is 0, and if we plug in, say, n equals 1 and n equals 3 into our revenue function, the 200 minus 100n, I can see that when n is 1, we get a positive result, and when n is 3, 200 minus 300 would be a negative result. So the revenue itself is going up and then down. We have a maximum at n equals 2. And we haven't done a lot using the second derivative, so I'd like to take a moment just to point this out, that if we look at the second derivative, we take the derivative of 200 minus 100n, and we just get negative 100, which is negative. So r is concave down at n, well, everywhere. So especially at n equals 2. So let's think about what that picture means. We've got a function where at n equals 2, we've got a first derivative equal to 0. So we've got that horizontal tangent. And then in combination with that, we need a concave down function. So in order to be concave down and have that 0 tangent, we're going to look something like this little bit of graph here. And that says that we have a max. So that's actually the second derivative test. If you've got the first derivative equal to 0, if you've got a critical point, and you're concave down, then you've got yourself a max. If you've got a first derivative equal to 0 and you're concave up, then you've got yourself a min. I'll make a point to go over that more in the next section. But that wraps up 3.3.